Good evening, ma'am.
Yes. I'm not able to hear. Selena, good evening.
Good evening,
Selena,
ma'am.
good evening. Ketana,
Good evening, ma'am.
good evening.
கேக்குது.
கேக்குதா? Okay,
Good
ma.
evening, ma'am.
Yesterday, we were looking at the definition of approximation algorithm, and I said we will look into some examples also. So, when we are looking at examples, I have talked about the problem called vertex cover problem, correct?
Yes, ma'am.
You are able to see my screen?
Yes, ma'am.
Okay. So what is a vertex cover problem? It is in a graph which is undirected. What we want to find? We want a subset of V such that at least one vertex of every edge of G belongs to C. So here the thing is, it's easy to find a C subset, but the challenge here is you need to find C in such a way that the modulus of C is very, very minimal. So the goal is to minimize the modulus of C. So for that, we were trying to define the problem, we were trying to understand the problem. So let me again show you what actually, when we look at this graph, what I think is a solution to the given problem. Okay. So now, what if you look at this graph, it consists of many vertices, namely 7 vertices and some edges. And I need to find a subset of this set of vertices such a way that all the edges has an input in it, or either the head or the tail of every edge is present in the new set C that I am forming. So how do we do it? The simplest and the trivial solution is to have the set of vertices of the original graph itself as C. So that is let's say the diagram B shows. When you look at the diagram C, so you have 4 different vertices which are in red, 3 are in black. These 4 different vertices will form the set C. Is it correct? If you look at it, so the first edge, so here this edge is being connected by this. So how about this edge? That is also you have a starting point here. And this edge, of course, both starting and ending point are belonging to the new set C. How about this edge? It has an origin here. How about this edge? It has an origin here. How about this edge? It has both the vertices in the set that we form. This edge, a destination is here. For this edge, again, the destination is present in the new C. So this is one solution. But then again, you can look at the next solution also here. So these are again, we are having 4 in number, but they are different vertices. Is it okay? Now the problem is clear, and what the solution we are supposed to get is clear. Hello. Hello. Kekudama?
No.
Yes,
ma'am.
no? You are
Yes,
able to
ma'am.
hear?
Ma'am.
Okay.
Yes,
Shall I move
ma'am.
on? So,
Yes,
Yes.
ma'am.
okay. So for this, I want to write an algorithm. So the algorithm actually is going to be an approximation algorithm. What we do is we take an edge. So for that, you have the starting point, ending point. You put that in your new set C. So now remove all the edges that is either having an either starting point or ending point of this particular set that we have formed now. See, for example, if you're going to consider the edge, maybe this. So now this I call it as A, this I call it as B, right? So the set C is going to contain A comma B. Is that okay?
Mm.
Now I can delete, maybe I'll name the edges, maybe you can, we will be able to see C, D, E, F, G, and a H. So now I can remove AC, correct?
Mm.
Shall I remove AC? Can I remove AC? Please respond. Can I remove AC? Can I remove AC?
Yes, ma'am.
Okay. So what other edge I can remove?
BD.
Yes. Actually this edge I can remove, and this edge also I can
BD.
remove. Yes, I can remove that also. Good. So now these two edges can be removed.
EB and
Yeah, AB and AC removed. This also is removed. So now we are left with the remaining edges. Among that, you choose one more. So here, this is removed, this is removed, this is removed. And can I select, maybe I select some randomly FG. I select randomly FG, that also which belongs to this. So if I am going to select FG, I can remove this, I can remove this, I can remove this. Already this is being included. Yes, no? Yes, can I do that? Okay. So this
Yes, ma'am.
also have been removed already because it has B, with B it has an origin over there. So we are left with CD and DE. So if I include, suppose I say CD, right? So if I include CD, then I can remove obviously DE. Yes, என்னாச்சு ஆமா எல்லாத்தையும் எடுத்துட்டு வந்தோம் சரி சரி okay, sorry girls. So now actually this is my set C. How many vertices it has got? 3 plus 3, 6 vertices it has got, which is not really an optimal solution, but it is a better solution than the solution of B. Is that okay? Hello? Hello? Hello?
Yes, ma'am.
yes, ma'am.
Yes?
Yes, ma'am.
Okay. So now, so this is all the algorithm is about. But so that means the starting edge which I am considering, depending on that, actually how many edges I am going to have will be varied. Is it right? Okay. So let me move on to the algorithm. So the algorithm is C is initially empty. Pick any edge U comma V belongs to E, and that edge, all that vertices to the set C. So remove all the edges incident on either U or V from E. So repeat the process till all the edges are removed from E and return C. Okay. Is there any question on this algorithm? Whatever we have done, we have put it over there. Is it okay? Is it okay? Yes.
Ma'am, we are unable to hear, ma'am. Actually, the voice is breaking continuously, ma'am.
அப்படியா? Okay, now is it okay? Now is it okay?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, you are able to see the screen?
Yes, ma'am.
Okay. So what do we do in this greedy algorithm one? We just initialize the set C with emptiness. So it's a null set we consider. Any edge you pick, so that which belongs to the set E, and it has starting vertex and ending vertex. Maybe I call it as U comma V. That you add it to C. So now remove all the edges that is incident either on U or on V, and now from E. So now repeat this process till you exhaust all the edges from E. So the answer is in C. So that's what I have done just before. Yes or no? Yes, you are
Yes,
able to
ma'am.
hear? Okay.
Yes, ma'am.
Okay. So now what I want you to realize is how many, what will be the running time of this particular algorithm? It depends on what? The number of vertices? Depends on the number of vertices or number of edges? Hello. 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 You're able to hear me? You're able to hear me? You're able to hear me, ma?
Yes, ma'am.
Okay. So now how much time will it take for this algorithm? That's what my question is. It's going to be dependent on the number of edges that you are going to have. Yes or no?
Yes,
Hello.
ma'am.
Yes.
Yes, ma'am. Yes,
Yeah.
ma'am.
So it is going to be the number of edges in the graph that you are going to have. That many times we may be at the maximum. We will be repeating. Maybe it may be minimal less than that, because if you are going to remove the edges, then there is a very good possibility it will not be reaching the number of edges. But the worst case only it will reach the number of edges. Is that okay? So so that means the number of edges is going to, for any graph is going to be finite and it is countable. So the algorithm will run on polynomial time. Okay. But now let us look into another example of this particular algorithm. So you look at this graph. So now initially we choose, maybe I call this the vertex A and B. The edge A comma B, A, B, I will choose. So that means obviously I can remove this and I can remove this. So that is what's shown in dotted lines here. Is that okay? Then let me choose this edge, maybe I call it as C and D. So when I choose C and D to be in my the vertex set C, I can remove this edge, this edge. So, and earlier actually I missed out this. So all these 5 edges have been removed. Now, so that means 1, 2, 3, 4, A, B, C, D is in my the set C. Is it okay? So now I'm left with these 2 and this one. So those have to be included. How do I include? I have to include this particular edge. So that's what is happening here. So that you include. And so now you will be able to see all the vertices that actually in blue color will give a solution. So this is giving us how many vertices? 4 plus 2? 6 in the set. But if there is another way by which it can be done, here when you look at it, A, B, C, which can form the set C, which is the vertex set of this given graph. So because here it is connected, here it is connected, these 2 edges are being connected by B, these 3 edges are being connected by C, and of course this is also connected by C. So this is an optimal solution, but this is a solution that I get using the algorithm that was proposed. Is that okay?
Yes,
Shall we
ma'am.
move on?
Yes, ma'am.
Okay. So now, you look at this graph. This graph is the one which I was talking on that day about when I have started the lecture, bipartite graph. So you have set of vertices on the left hand side, another set of vertices on the right hand side. You will see that all the edges are going from left to right. There is no interlink within the set A or within the set B. So this is called bipartite graph. And if that is happening with each and every edge, then we call it as a complete bipartite graph. Okay. So, but anyway, I'm not interested in getting into bipartite graph. But if this is going to be the kind of graph that I'm going to find, for which I'm trying to find the vertex, if there are n vertices present in the graph, my C will contain, hello, 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 Hello.
Hello.
Yes. How
Yes,
many?
ma'am.
What will be the number of vertices that will be present in C if it is going to be a bipartite graph like this? On the left hand side, you have 1, 2, 3 up to n. On the right hand side, you have 1, 2, 3 up to n. So now, when you are finding the vertex cover, what will be the cardinality of the vertex cover?
2n, ma'am.
2n is total. So my vertex cover will contain half
2n.
of it because either I have to take it from the left or I have to take everything from the right. So that will be my optimal solution. Okay. So the optimal solution. So actually here itself it is shown, no? The size of the maximal matching graph of this is going to be n. That is modulus of m is going to be n. Our algorithm always produces the cover of C of size 2n. So, but anyway, we can get it as n. So this is one example. Actually, this will lead us to think something differently. That is going to be, we should not depend on the edges. Why can't I depend on the vertices? So what I suggest is, when I'm going to depend on the vertices, so you choose a vertex which has got the maximum degree, so that you can remove so many edges. That's what our intuition says, right? So initialize your C, set C to be an empty, take a vertex V which has a maximum degree, add that to your C. So now remove all the edges which is incident on V from E. So repeat this process till all the edges are removed from E. And then, of course, we can return the set C. Is that okay? Earlier, we are dependent on the edges. We were choosing the edges. Now what do? We are choosing a vertex which has a highest degree. Right? That's actually making sense. So if you're choosing that, we can remove so many edges and it will be actually forming a better solution. So that's why we do that. So then after removing the edges, try to find the next vertex which has a maximum degree, try to include that, repeat the process, and then finally you return C. Here again, the earlier case, that algorithm, the number of times we repeat the process will be at the maximum, that is equal to the number of edges. But here it will be equal to number of the vertices. Is it right?
Vertex.
Yes, good. Who is
Yes,
it?
ma'am.
Who is it? Who is that? Okay. Now, this is what graph? What graph is it? What graph, please answer?
Bipartite.
Yes, bipartite graph, but it is not complete because you can see, so from here to this, from here to this, and all, you don't have the edges drawn. So you don't, since you don't have for each and every vertex, you should have one edge. Then I call it as complete bipartite. But here some vertices does not have that property. So that's why I won't call it as complete bipartite, it's just a bipartite graph. So in this, let us apply this algorithm, whatever we have learned. So maybe I name it as which vertex you will choose? Which vertex will you choose? I'm naming them. Let me know.
G and H.
G and H. Okay, good. So for sure, these we will not choose, right? Because it has got a degree to be only 1. All these 4 has got degree to be 1. So we will not choose. We can choose these, any one of this, and maybe this is only 3. Okay, this is only again 3. Okay, so we choose any one of them. remove those. Actually, there are also only three. So you can choose G or H or A or B or D also you can choose. Anyone you can choose and then remove those edges which are originating from that vertex. See, if you are going to choose A, then remove this, remove this, remove this. Like that you can do it. Then apply, then you include B. So remove all the edges which are originating from B. So like that I can keep on doing it. I will have the resultant set C. So that is going to be the vertex cover of this given graph. Is that okay?
Yes, ma'am.
Okay. So now let us okay. You can see the execution. You are able to see the first, this vertex is included, 3 edges are removed. My connection is very poor. So then next this vertex is included, the edges are getting removed. Yeah, you're able to
Yes,
see.
ma'am.
Okay,
Yes, ma'am.
yes. Then you see where it goes. See, since all these are being removed, so actually it has to include on this side all these 4 which had degree to be 1. Is that okay?
1. Yes,
Yeah.
ma'am.
Okay. Shall I proceed?
Yes, ma'am. Yes, ma'am.
Okay. So now, when you look at the vertices picked by the algorithm forms a vector cover. This algorithm is in a polynomial time of the input size. So already I said that it's going to be dependent on the number of vertices that you are going to have according to this
Number
algorithm.
of vertices.
Number of vertices. So optimum solution contains of all the vertices, which is going maybe at the maximum it can go up to k factorial. We are looking at anyway. We don't bother much about it. So now that actually discussion on vertex cover problem is over. Is that okay? So what is a vertex cover problem? I need to find for a given graph the set C, which is a subset of V, which will